Today is basically, as I mentioned in the email, it's for entertainment only. It's not going to be part of the exam. But I think, shame there's only 20 of us, it's probably the most interesting of the lectures. So just thought I'd give us a bit of inspiration at the beginning, picture of Albert Einstein. And one of the things that, kind of obviously when things are taught at university, you don't get everything in the perfect order historically and so on. And you get taught, year one special relativity about, the Lorentz transform. And you quite often get the impression that, Albert Einstein was this bloke who just kind of thought up completely new ideas about space-time. Well, where did he get them from? The big clue is what we now call the Special Relativity paper of 1905. You'll see its title is On the Electrodynamics of Moving Bodies, or the original, of course, Einstein wrote in German, Elektrodynamik bewegter Körper. And we're going to have a look today at what Einstein did in a kind of slightly backhanded way. I'm going to show that basically when you have one quite simple situation, you definitely need relativity to make sense of it. And the obvious situation that I'm going to treat, it's not so obvious at first, but it's just a current carrying wire. So imagine, first of all, I need a reliable keeper of space-time for the students. Anyone? Harry, you look a reliable chap. There you are. There. Have a meter ruler and have a clock. So that is going to be the stationary body in this lecture. I am going to move around a bit, and I've got a meter ruler and a clock. Now, the situation that I'm going to consider, this is a double-purpose meter ruler. First of all, let's consider that I've got a current-carrying wire just going down the lecture theatre like this. And now we know, and we've done this to death in the steady state magnetism, we know exactly how to calculate the magnetic field of a current carrying wire. So we did that in one of the early lectures on Ampere's law, and we know perfectly well that the magnetic field is going to be circulating. So if again, right hand screw rule, if I've got conventional positive current flowing down this way, I'm going to have field lines circulating. And I know perfectly well that the magnetic field produced is going to be given by this formula. So we've got that B, we'll assume it's tangential rather than just writing it out as a vector. We know it's going to be mu naught over 2 pi I over r. And of course, if I want, I could write this as an epsilon naught c squared I over r because of the unification theory. So, and you think, well, that's a very, very straightforward thing. This doesn't look like it's got much to do with relativity. But now let's say I fire an electron along exactly the same direction as the wire. Yeah. So now the magnetic field is circulating. So, for example, at this point, it's pointing this way. As it's going around, we've got the magnetic field pointing in towards the board. I now fire the electron at right angles to it, and the direction, of course, that's at right angles to both is this one. And if you get your cross product right, you get that the electron is accelerated towards the wire. So again, we're using, and it's been underlined, we haven't done so much on the force law, but if you look at this table, which quite amazingly summarises basically the whole of physics known up to 1900, apart perhaps from the thermal and statistical side of physics, but certainly if you like the pure physics, well, we've been studying these 4 equations all term, including charge conservation, which is put in brackets because that's already contained, as we know, in the Ampere-Maxwell law. That's why we had to incorporate this second term. But now let's think about the force law, that the force is equal to Q E plus V cross B. Now clearly in this term, in your reference frame certainly, that wire is not charged. no charge at all, but it is producing a magnetic field, and you can see that the cross product of the magnetic field, which is pointing this way, as we get, of course, we could have different orientations at different angles, it produces an acceleration towards the wire. So we've got this magnetic field, and we've also got that F, oh, sorry, blue chalk's probably not the best bet, F is equal to Q V cross B. So we've got a very straightforward situation here where there's the current carrying wire, and we fire an electron exactly parallel to the wire, and because of the geometry of this, we observe an acceleration towards the wire. So you'll see the electron perform a parabola. Again, at your level of maths, extremely easy. We've got uniform translation in this direction, uniform acceleration in this direction, so we get a parabola. And it's because these are at right angles to each other, the magnitude of this force down towards the wire is equal just to QVB. And of course, I can say straightforwardly, well, that is now 1 over 2 pi epsilon naught c squared I over r. That's my magnetic field B times Q times V. And that's precisely what you would expect to observe and what you would observe. So if you could see an individual electron as it went across, it would simply form a parabola and hit the wire. Now, of course, I'm a physics lecturer, so I'm going to be awkward. I'm entitled, of course, you've analysed the physics correctly, and let's say this is all in reference frame S, S for student, and we've got a very reliable man with his space-time there, and he's at rest, and he's observed these phenomena. But now, I'm perfectly entitled to any other Galilean reference frame, and if I excuse me, if I'm in an inertial frame, I am now going to walk along at the same speed as the electron. Yeah? So in fact, that's exactly what I'm doing. I'm walking across at the same speed as the electron. So in the awkward person, I don't usually think of myself as Martin, but actually S goes very well with my surname. So S prime, I have that V is equal to naught. I'm perfectly entitled to walk along with the electron and say, well, actually, in my frame of reference, this electron isn't moving. It's completely static because I'm moving with it. And so I don't appreciate any velocity. To me, the electron just looks completely static. And now you think, well, there's going to be a bit of a trouble here because in my reference frame, the electron is completely static, and so F, which is equal to V cross B, is 0. So, dear, the electron doesn't experience any force whatsoever. So you might think that physics is going to go horribly wrong, because in your reference frame, you see the electron performing a parabola. Sure, in my reference frame, it wouldn't have any velocity along this axis, it would just be at rest, but it seems that I don't see any force at all towards the wire. So just depending on which inertial frame we choose, we would appear to get completely different physics. And that is against the principle of relativity. We're both in straightforward inertial reference frames, but we seem to see different physical phenomena. You see the electron curving in towards the wire. I don't see any force at all. I just see it drift across the lecture theatre. It's a nasty one, isn't it? We're in trouble here. Physics is, but we're not in trouble, because it seems very odd at first. Basically, there is an electric field in my coordinate system. Now you might think, well, no, that's ridiculous, that wire's not charged. But before we can investigate what's going on, we need to consider what's going on inside the wire. So there's your reference frame. This is actually figure 106 of the course handout, but that I've done it up in colour because it makes it a little bit easier. So what you see in your reference frame, the wire's at rest. Well, what does that mean? That means that the iron cores are at rest in your reference frame. The actual copper iron, you know, so if we look inside the wire, let's say it's an ordinary copper wire, like we've got, most of our wires are made of copper. Well, of course, inside the wire, we've got these copper plus kind of iron cores, and you know, you'll have done this in solid state physics, things like the Drude model. The light electrons are just, the conduction electrons are just drifting relative to these cores. So in your reference frame, and as I say, you're perfectly entitled to do this, and you've analysed the physics correctly, this is indeed the force, and you do indeed see a parabola. You've got the situation where the iron cores are at rest, and that's represented by rho plus. That is the density in coulombs per cubic metre of the iron cores, and in your reference frame, well, their velocity is definitely naught. In your reference frame, the negative charges, represented here by the iron density rho minus, are moving with some velocity v. And so you've got a current flowing in the conventional sense in the opposite direction. Now in your reference frame, this electron, which is fired parallel to the wire with some velocity v naught, negatively charged, curls in this parabola towards the wire. So in your reference frame, the wire's at rest and the particle, the electron, is moving. However, in my reference frame, things look very different. Because I'm drifting along at the same speed, and actually I can do that. You're probably aware, although electromagnetic waves travel at the speed of light, electrons really do travel very slowly down a wire. They're making constantly, if you like, collisions with the iron cores and being scattered. And they, you know, even at my age, I can jog along as fast as an electron in a wire. So it's not particularly unrealistic for me at just at an ordinary speed to say, well, that electron is at rest. But now I have to interpret what's going on inside the wire very differently as well, because in my reference frame, the electrons in the wire are at rest. And again, I'm going to take particularly, there's a certain, I'm going to associate with this current some, if you like, drift velocity of electrons in the wire. And of course I could fire my electron at a different velocity v naught. The way to handle that's in that electromagnetic field tensor lecture, which I've omitted and which I'll do for you interested young scientists who turn up at the end of term. I'll do that after the exams because I think it's a very big shame. We used to have third year EM and fourth year EM theory, so otherwise you wouldn't see this at all because we don't have those courses anymore. I'm going to take the particular case, and we could choose it, that the drift velocity is equal to v naught, because that just makes all the maths easier. We don't have to worry. I mean, all the principles are the same. I've got some electrons which are in your reference frame, the electrons are drifting down the wire, and I fire this other electron parallel. Well, I can certainly choose as a special case that these two velocities are the same as each other. So just to make the maths easier and bring out all the principles, I'm going to assume that the drift velocity of the charge carriers inside the wire is the same as the velocity with which I fire the electron parallel to the wire. So, however, in my reference frame, things are looking very, very different because I now see the electrons in the wire at rest and I see the iron cores moving in the opposite direction at some velocity v. So in doing that, again, first of all, I want to now convert this expression here. I want to convert the current into the drift velocity of the electrons in the wire. And again, we've done this several times. Most recently, it's still got the scribbles on it from the pointing vector lecture. But if you go back to the original idea of figure 43, The whole point, in a way, was to prove that, and again, it just makes sense from dimensional analysis, that the current in a wire is the current, the charge density times the velocity times the cross-sectional area of the wire. And we just get that by considering, if you like, a lump of charge being moved along at some velocity v. So I can certainly replace the current by rho VA. And so continuing this blackboard, as I say, this is your reference frame, you're analysing the physics. You would replace this by, this is the charge on the electron that's been fired into the field. You would replace this thing with rho VA. Make sure I get my expression here correct. And again, at the moment, if you want to catch up more with you know, I'm just going to go through this informally. These are the notes that are on the VLE. We just consider the Lorentz force, and we've already done that. We now, again, I've rewritten this. Of course, I can replace by 2/4. And now I'm just coming to this point here. So I've simply replaced the current in that expression. I'll leave this as a 2 here, rather than writing it as a 2/4. I was probably being a bit over clever here, writing this as a 1/4 pi epsilon naught, just to emphasise that the force to me is going to look like an electrical force. But you can see that that's obviously the correct expression in your framework, and just by straightforward analysis, I can put in rho minus VA, and then I've got the expression. So in your frame of reference, the force towards the wire is 1/2 pi epsilon naught c squared, and then rho minus, because you're interpreting it as the drift of the electrons, times q. So there's my current, there's my rho, there's my q, and you'll see I've got a v squared here, and I've got, excuse me, that's the cross-sectional area with a capital A, the cross-sectional area here all over R. Yeah, and again, you begin to see where the relativistic effects are already kind of emerging. If we write it in this way, we've got a v squared over c squared in this expression here. So this will, again, you can consider the general case where the drift velocity of the electrons and the velocity of the electron that's fired into the field are different, but that really doesn't, as I say, teach us anything new. So I've written it in this way here. So again, it's a slight rearrangement. Let's write the q here over the 2 pi epsilon naught, and we'll write the v squared over c squared here. Here's my v squared over c squared, and then the rho minus times the area and divided by the distance. So that's all very, very straightforward analysis in your reference frame. But now, what about my reference frame? And that is the one here. Well, the very important part, and it's very strange at first to get used to this, the way things work is, although that wire is not charged, in my reference frame it has a non-zero charge density. And this is the crucial point of the whole treatment, really, is that the wire has got a charge density, and I'm going to calculate the electric force in my frame and show, well, let's not spoil the party too soon, something similar to this expression here that you see as a magnetic force. So let me just elaborate on that with a second view graph. Well, remember, in your reference frame, the wire's at rest and the particle's moving, so the charge, let's say, is in some length L0 in your system, and there's the cross-sectional area A. Well, I'm moving relative to you, and so it's perfectly clear that actually my meter rod is not the same length as Harry's meter rod. I'm in a moving frame relative to that static meter ruler that's lying there. So I don't have the ability to say that the volume is the same. So in my system, S prime, where I'm moving, this L prime is emphatically not equal to your L0. It's a Lorentz contracted distance. And we know again, as I say, we're going anti-historically. It's sort of the electrodynamics produce relativity, but we're going to show that you need relativity to understand even this simple case. And I know perfectly well that and let's make the x coordinate the one across the lecture theatre, that my ruler is contracted relative to Harry's ruler by the factor 1 minus the steady drift velocity divided by c squared. So I know that I have got a different length in my system compared with yours. So if you go through, let's go back. So again to the lecture notes on this, the length in my system of the wire is equal to L naught times the square root of 1 minus v squared over. So remember, the cross-sectional area is not changed. The dimensions transverse to the motion aren't changed. Again, you know, if we've chosen the x-axis to be the axis of motion, well, clearly y prime and z prime are just equal to y and z. So the cross-sectional area of the wire is equal in both cases. It's just the distance is different. So now the charge, because, and again, say this is a very subtle, and at first when you see it, quite difficult point to appreciate, and if, as I say, in a sense, the crux of the whole matter is that the charge is the same. Now you are judging in your rest system that the total charge Q in a certain length of the wire is the charge density, obviously times the volume, which is L times A naught. So, but charge is completely conserved. So in my system, I get, because the charge is conserved and the cross-sectional area is not changed, I get that rho L is rho naught L naught. So if I combine equation 9(7) with conservation of charge, I get that the charge density is rho naught over the square root of 1 minus v squared over c squared. And it's quite that's a nice result, and one that, in a sense, you might expect, because if you like, again, we've got, I'll come to this later, the implications of all this for mechanics. The mass is equal to m naught over 1 minus v squared over c squared. So the charge density transforms like the relativistic mass of a particle. So in my system, in S prime, remember, in my system, let me just go back to the picture. In my system, these charges, these ion cores are moving, yeah, whereas in your system, they were at rest. So the way round that the Lorentz transform works is that in my system, L naught is actually, these charges in my system experience a Lorentz contraction. Yeah. So, but it's the other way round if you look at the negative charges, because in your system they were moving, but in my system they're at rest. So when I maybe try and put these two, this might be a bit of a, we'll see, yeah, let's try and get them on the same page. So for the positive charges, the Lorentz transform is as in equation 9(9), but for the negatives, it's the other way round. Obviously, in one system, in your system, the positives are at rest and the negatives are moving. In my system, the negatives are at rest and the positives are moving. So the Lorentz contraction is an expansion for the opposite set of charges. So now, when I take the total charge density in my system and add up those two formulae, I have got that in my system, the primed coordinate system, the two charge densities that I have to add up are rho plus over 1 minus v squared over c squared plus rho minus times the square root of 1 minus v squared over c squared, because the Lorentz contractions are working in opposite directions for these two. So I then get, and again, some of the steps on the calculation are missed out, but this is a particularly easy one. Again, you've got now the possibility here of simply adding these up, but clearly the net charge density is the sum of the positives and the negatives. And because you remember the stationary wire is neutral, you've judged correctly that the stationary wire is neutral. I can replace rho minus with minus rho plus. Wouldn't be a neutral wire if that wasn't the case. So that my rho prime, so in my coordinate system, the charge density is equal to rho plus over the square root of 1 minus v squared over c squared minus rho plus, I'm just replacing this by the neutrality of the wire in your system, is times this square root 1 minus v squared over c squared. Well, clearly I can take out, let's just move this up a bit, I can take out my rho plus over the square root of square root sign, 1 minus v squared over c squared, and then that's into 1 minus, and then if I've taken this into the outside in the denominator, this is left as 1 minus 1 minus v squared over c squared. Oops, let's close the bracket here. So, if you like, I've just multiplied numerator and denominator here by the square root of 1 minus v squared over c squared. And of course this term cancels with this one, two minus signs, v squared over c squared times rho plus over the square root of 1 minus v squared over c squared. So I see a non-zero charge density in my system. It's a really tricky point and I'm actually using the fact that the total charge in a given volume is conserved, but I'm looking at it from this different point of view. So I've got a non-zero charge density. So now we can begin to see, I'll do it quantitatively in a minute, well, this is a charged particle, it's an electron, this is a positively charged wire, I am going to see the electron attracted to the wire. Am I going to see, though, the same force that you saw in your system? And let's do that next. Going backwards rather than forwards, my usual view graph. They're all in here somewhere. It was a bit of a... Went out celebrating with some BSc project students yesterday afternoon after they'd finished their handing in, which is not done the best for my notes, it has to be said, but they're in here somewhere. So we've got a situation now where we've got the electric field and we've got to analyse in my system, I've got to analyse the electric field, and of course I'll analyse it by Gauss's law. So again, I've brought back, again, it's one of these things that you'll have done many times with Kieran, is analysing the electric field by Gauss's law for a line charge. Because remember now, this current carrying wire, to me, is looking as if it's charged, and so I want to calculate the electric field that it's producing. Yeah? And the electric field it's producing is given very simply by Gauss's theorem that we know that the electric field is lambda, which is the charge per unit length, over 2 pi epsilon naught r. And obviously lambda, the charge per unit length, is the charge density rho times the area. So this is an already analysed problem. Once I've got this charge density here, in my system, I can then calculate from that an electric field. So I've got my charge density, and it's producing a radial electric field from the wire in my system, which is equal to, well, there's my rho, which is rho plus over 1 minus square root of 1 minus v squared over c squared times v squared over c squared. That's my charge density. So I've got to multiply it by the area and divide by 2 pi epsilon naught r in order to get the electric field which is being produced in the moving coordinate system. So I multiply this by A and then simply divide by 2 pi epsilon naught r. So in my system, the electron is at rest, but it experiences this electrical attraction, which I've rewritten here. It's obviously the same formula as the charge density times the area times v squared over c squared times 2 pi divided by 2 pi epsilon naught r times this square root term. So if I rewrite that in these terms, I get a force. Of course, in my system, the Lorentz force, I see no magnetic force at all. In my system, the electron isn't moving, so the V is naught, and I experience simply the charge times the electric field. So that's the electric field in my system. So the force in my system is just Q times this. And now we can do our comparison. You've calculated the magnetic force in your system. Let's bring it back down. And we'll compare these expressions. Well, again, it doesn't matter. In the static, remember, these are not primed. These are in the same system in which the wire is neutral. So these two rows are certainly equal to each other. So the charge density of the wire in the system in which the wire is at rest is there. The cross-sectional area of the wire is clearly there. This factor v squared over c squared is clearly there. The 1 over r dependence, I see that because it's the 1 over r dependence to me becomes a lot because of a line charge giving a 1 over r electric field. To you, you got the 1 over r dependence on that side by considering the B being equal to mu naught over 2 pi I over r. So certainly this is just the distance from the wire. This is the charge on the particle which is fired into the field, which is certainly the same. And we've got here the factor 2 pi epsilon naught in both equations. And you think, oh no, we're out. Bugger. All right, well, let's pack up. Physics is totally finished. Relativity doesn't work. Because, you see, the thing is, in my system, you would definitely expect me to see, because I'm moving with the wire and you saw, with the electron, and you saw a parabola, you'd expect to see an identical force in towards the wire, except in my system I just see the electron fall directly to the wire because I'm moving along with it. And if it's a different force, oh dear, we're going to see different physics. It's going to hit the wire at a different point at a different time. However, all is not lost. Harry is also keeping a clock, and so am I. And is my clock going at the same rate as Harry's clock? No, emphatically not. So my clock is also ticking at a different rate. We've analysed the physics completely correctly, and we're out by a factor in the primed coordinate system. The force appears to be reduced by this factor here, this square root 1 minus v squared over c squared in the denominator, and as, well, increased in effect because v can never equal c, so this is going to be less than 1. And so we've got a different problem now, because I also know, if I could find, I mean, I'm sure you know the Lorentz expression, my clock is actually also ticking at a rate which depends on this square root 1 minus v squared over c squared. So what I actually want to measure is the change of momentum. Now, we've got different forces. Just move this up and out the way a bit. And we're out by this factor. But what we're really interested in is, and we've made x the direction going across. Let's make y the direction towards the wire. What I really want to know is the change in momentum in y direction in the two systems. So I still got that my force is equal to dp by dt, the rate of change of momentum, but they're in two different systems with regard to time. So that now is the crucial point, again, that we've now got, in comparing these two expressions for the forces in the two coordinate systems, we've got a difference in factor of that circled 1 minus v squared over c squared there. So we can write that the force in the prime system is the force in the unprimed system, your system at rest, divided by the square root of 1 minus v squared over c squared. However, now we're coming to the point about the clock. So we've still got, if we call the transverse coordinate y, what we really want to compare is the change in the y momentum in the two coordinate systems. Now we've still got the equation that f is dp by dt, but the change in momentum, and let's make it over some small but finite time, the change in momentum is the force times delta t in your system, but the change in momentum in my system is the force in my system times delta t in my system. And my clock is running at square root 1 minus v squared over c squared, slower than yours. So I also have a transformation between the unprimed and the primed systems, a Lorentz transformation of the time. And so if I then take, finally, the ratio of the change in transverse momentum in the two systems, it's the f prime delta t prime over the f delta t. The factors square root of 1 minus v squared over c squared cancel, and the answer is just equal to 1. So we do see the identical physics in the two systems. Of course, because I'm moving along with the electron, I just see it accelerate uniformly into the wire with exactly this force here. You've interpreted it as a magnetic force. So if you like, the whole point of this is that what we call an electric and what we call a magnetic field depends on our frame of reference. And this is indeed how, if you like, the relativity was discovered in the first place. You've interpreted entirely correctly the whole phenomenon in terms of a magnetic field produced by a current carrying wire. I've interpreted it entirely correctly as the electric field produced by a wire which is not at rest. In my system, the electrons at rest, but we get identical forces towards the wire, and so we do observe the identical physics. So this is a very, very beautiful illustration. Again, I cribbed, like a lot of my lectures, from the Feynman lectures, that if we thus, this is the crucial point, we get the same physical result whether we analyse the motion in a coordinate system with respect to the wire or with respect to the particle. In the first instance, you got this purely magnetic force. In the second instance, you get a purely electric force. Now, if I had chosen some intermediate coordinate system. I don't have to move at exactly the same speed as the electron. It could kind of be going a bit faster than me. You know, I had too many cigarettes for breakfast and couldn't catch up with it. Then, of course, I'd see a mixture. That's the two extreme cases of pure magnetism and pure electricity. I'd actually, in a different coordinate system, see a mixture of electric and magnetic fields. Now, it's funny because some people say, and magnetism is just a relativistic effect of electricity. And in a sense, it is that you can say for a current carrying wire, basically, the magnetism is, you could go to another frame of reference and say it's just because electrons are moving relative to iron cores, if you like, you could say the wire has got an effective charge, because you cannot have them both at rest. Either the charge carriers are moving or the iron cores are moving. Wouldn't be a current otherwise. Therefore, they're in different volumes. They've got the same charge, but they're in different volumes, so they've got different charge densities. Now, this phenomenon, again, I'll just give you a heads up, because we've still got 10 minutes of how one analyses it in general. But also, just a word of warning, when people do this exam, they get really excited and think, I proved that magnetism's just a relativistic effect of electricity. It's not. There is no coordinate system you can go to that will transform away the fact that in an electromagnetic wave, for example, a light wave, you've got to have electric and magnetic field vectors. This was a slow-moving example where an electron was sort of like bobbling along the wire at jogging speed. We can choose a coordinate system that totally transforms the magnetic part of the field away. We can just calculate purely with electricity and say that magnetism is just due to electricity in a moving coordinate frame. But you emphatically cannot go to any coordinate frame in which you make the electromagnetic field of a wave, all the magnetic components disappear. I mean, if you like, of course in an electromagnetic wave, the electric and magnetic field vectors are moving at the speed of light. So you've got to be a bit careful that it's just an effect of, if you like, magnetism, just an effect of electricity. So there is a relativity of the fields. Now, you might think that this is now completely and totally irrelevant. I'm going to talk for a couple of minutes about the angular momentum of a rotating object. And I've got a great big disk, and it's whirring around some axis. And you're probably done to death the idea that the angular momentum of this system is given by the cross product of, you've got to multiply by the scalar mass of the position vector and the velocity vector. Now, I've mentioned, I might have even mentioned it in the first year maths last time, that a cross product is what's called an axial vector, and it's not a real vector. It's a pseudo vector. And I mentioned before, I mean, if this is the xy plane and I've got an enormous great big disk rotating in this plane, it seems ridiculous that the angular momentum is along the z-axis. And if you look at this cross product, of course it is. The only non-zero component of the cross product in this particular example is going to be the k, which is an xvy minus a yvx, which is emphatically non-zero. So, in fact, all cross products are what are called antisymmetric second-rank tensors. And truly, when you write a cross product, it should be written, and it looks like a matrix, and I know you've done a little bit of tensor algebra in the maths. It looks like a matrix, but the components transform in a particular way under axis transformations. And so you think, well, if I take the cross product by writing it out in this way as a tensor, it's a three-dimensional tensor because space has got 3 dimensions. It's a second-rank tensor because you need 2 indices. And especially, cross products are antisymmetric tensors. And antisymmetric means that, as I say, I'll develop this more if anyone's interested in coming along at the end. antisymmetric means Lij is equal to Lji with a minus sign, antisymmetric. So if these two are equal, the only way Lxx can equal minus Lxx, or Lyy minus Lyy, or Lzz minus Lzz is precisely if they're equal to 0. And then, so the diagonal terms of an antisymmetric tensor are all equal to 0, and then the off-diagonal terms must be opposite to each other in pairs. Lxy is, so my Lyx I can write as minus Lxy, my Lzx I can write as minus Lzx, and my Lzy I can write as minus Lyz. And I've only got 3 independent components, and that's why it appears to behave like a vector. And it's a complete accident of 3-dimensional space. It's only in 3 dimensions that you would get this antisymmetry coming out as a sort of so-called pseudo-vector. Now it happens that this one transforms like the z component of a vector. This one transforms like the y component of a vector, and this one transforms like the x component of a vector. And this Lx, Ly, Lz is called a pseudo-vector because it's got 3 independent components that transform like a vector, but it is in reality an antisymmetric, second-rank, 3-dimensional tensor. And so you probably think, well, that had absolutely bugger all to do with the rest of the lecture. You know, Martin, he had 10 minutes left. He's just lobbed in a bit on something completely irrelevant. But the magnetic field is just like this. The magnetic field is inherently an axial vector. It has, and so it looks like a vector where this xy component transforms like the z component. This one is the y component, and this one here is the x component. And of course these are obtained just by the antisymmetry condition. So it's not like everything that I've told you is wrong by any means. It's perfectly okay to treat the Maxwell equations in vector notation. However, if you want to go to a deeper level, you need to go to this next step. And the full electromagnetic field tensor is, and this is written in a tensor way so that the x, y and z components transform in a rotated coordinate system into x prime, y prime and z prime like an ordinary vector, but you get the mixture of t and x or ty and tz by Lorentz transforms. So it mixes, this full field tensor contains all the symmetry of the 2 types of field. So first of all, if you take out the time component and you just look at a xyz component, you'll see that that is precisely what I was talking about. That's why it's relevant that the angular momentum tensor is just like a magnetic field tensor, and we interpret it, and we've interpreted it throughout the course as the x, y and z components of a vector. Likewise, if you simply take time out the game in this way, the electric field has got 3 independent components which transform in a particular way, but the full picture, and this is, was discovered by Einstein and then extended to gravitational theory. Gravitation is completely different. The gravitational field tensor is also a 4x4 tensor, but it's symmetric. And poor old Albert spent the last 30 years of his life trying to unify the two and never got there. But you'll see it's not like in 3D. When you've got a field tensor in space-time, then of course the diagonal components are all equal to 0, but now you've got 6 off-diagonal components, and they are our good old friends, the electric and the magnetic field. So if you want to go deep into, the theoretical side, this is a sort of stepping stone. For example, in the maths department, they do a very beautiful course on gravitation, Einstein's general theory of relativity, in the 4th year. And the thing I like about this is the only excuse I think I've ever had in my life to use 4 hyphenated words consecutively. Because this tensor, it's antisymmetric, that's clear. It's got this property of antisymmetry, always you get these pairs occurring. It's second rank, you certainly need 2 subscripts. In fact, this, in the more advanced way, you write f xt would be equal to ex. The whole thing is a tensor. So it's 4-dimensional because you've got 4 indices, and it's a space-time tensor. So it's an antisymmetric second rank 4-dimensional space-time tensor. And in 3 dimensions, this EX, EY, EZ transforms like a polar vector, and the BX, BY, BZ as an axial vector. And if you want to treat the general, I just treated this one particular case of where, for example, if you had to treat the case where the drift velocity of the electrons in the wire was different to the velocity with which the electron is fired into the field, you'd need to express everything in this kind of way. So but always, in a sense, it's only because we live in a slow-moving world that we see electricity and magnetism as separate effects at all. If we kind of saw, I don't know quite how you express this, if we saw in space-time, if we saw in 4 dimensions, we would just see a single object with 6 independent components, and it would just be an electromagnetic field tensor. So you have to be, my last word on it, I've got a couple more view graphs just from the course, is that what we've looked at is this case where in frame S the charge density is 0, that was your frame of reference, and you have a magnetic field circulating the wire, so if you fire something parallel it gets attracted to the wire by a magnetic effect. We know, and indeed this is why 2 current carrying wires attract each other. Each one of those, each charge carrier, if you think of the definition of the ampere, that's 2 current carrying wires attracting each other. That's how we define the SI unit of electromagnetism. And what is actually happening is that the electrons in wire 1 see a non-zero charge density in wire 2 and are attracted, and that vice versa. The electrons in wire 2 see a non-zero charge density in wire 1. So they pull on each other precisely because they don't see the parallel wire as being uncharged. And in the moving system, you have a different current density. I didn't go into this. Of course, in my system, there's a different magnetic field as well. But that's not relevant because I chose to walk at exactly the speed of the electron. Therefore, my V cross B was going to be equal to 0, even though my magnetic field is different. So the fact that my B prime in my system's different didn't make any difference in that particular case. And it's just a warning at the end, whenever you see pictures of field lines, obviously, whenever we draw an electric field, we say, oh, it's radial, it comes out from the charge. But, that depends on your frame of reference. That's in the frame of reference in which the charge is static. If I happen to be rushing towards the charge at 0.9 the speed of light, I'd see Lorentz contraction of the field lines in one direction, and the electric field would emphatically not be spherically symmetrical in that moving coordinate system. And likewise, you can get electric fields which appear and disappear completely in different coordinate systems. So I shall leave you with that mind-boggling idea. Wish you all a very nice Easter. And as I say, this was just for entertainment. You're not going to be tested on this, but if you want, I can do more on the field tensor after the exams. So I'll see you next term, right at the beginning. I think we're on Monday morning when we get back. So see you then and have fun. Harry.